Okay, thanks a lot. So thanks to all of you to come back to this second lecture. So this morning I essentially say some word about the ambiguities that can carry a bilevel problem, and even more about multi-leader follow games, which is kind of more tricky things. But I also tried to pursue you through the first application that nevertheless, even if it is challenging, or I should not say nevertheless, precisely because it is challenging, we have to go there. This is a place where new things has to be done, and new ideas can come and enlighten positively the difficulties that we can imagine now. So let me go directly to the example that I gave this morning, and I must start by giving my sincere apologies. I made it very rapidly, this example this morning, and when typesetting this just before the talk, I made a typo on the function. So if you try to do the example during lunchtime, I guess it was not so interesting. Here is the example. So the modification is here, actually, here, because what I wrote was a derivative, by the way. So that was not a good idea. So essentially, the idea is on this example is that we have a game with two players, two leaders, x1 and x2, player 1 and player 2. And there is a follower, one follower, deciding about a variable y with minimizing this function. And so each of the variable is positive, so between 0 and 1, and the function are those ones. So very simple things. And so if you go to the follower problem first, so you have this minimization, and thus if you solve it, you will have this solution map, which depend, of course, of x1, x2, and you have two possible solutions. So x1 plus x2 and minus x1 minus x2. So if you plug this into the leader one problem, then it means that the objective function will be so x1 y. It is the objective function of the first player, and so it will be this if y is equal to y1, and it will be this if y is equal to y2. And of course, the same for the response function of player one. Is optimal decision will be 0 if y is equal to y1, because here, in this case, the better choice is to put 0. And since we are minimizing, and here the better case, since here we will reach some negative things. I recall to you that x2 is positive, so it's to put 1. With a payoff of 0 and minus 1 minus x2 in the different situations. And if you have a look to the leader 2 problem, it's kind of symmetric because it's simply minus here. So you will have this kind of thing, and the response function will be thus here 1 and 0, and so with those payoff. Actually, I should not write it like that, because finally here what is wrong is that here, if I go back to my problem here. The initial problem, I said I decided to choose the optimistic approach. So if I choose the optimistic approach, it means that I am minimizing in x1 and in y. And since I have two possible y, I have to minimize also in y. And I cannot say simply the response function is x1. This is not totally correct. So instead of writing those response function, I should write actually this. That is, we have the couples 0 and y equal to y1, or 0 and 1 and y equal to y2, with a payoff of 0 in this case, and with a negative payoff, strictly negative payoff in this case. And for the other player, we have 1 and y1, and with a negative payoff, strictly negative payoff, and 0 and y2 with a 0 payoff. So looking to that, of course, what is clear is that the equilibrium, Nash equilibrium, will be 1-1, because then you will have the guarantee of a negative payoff here and the guarantee of a negative payoff here. So that seems to be great. But we have immediately a very terrible problem, is that here, okay, I take 1 here for x1, it is because I have y equal to y2. But if I take 1 for second player, it is because I take 1 equal y1. So I have a kind of Nash equilibrium, but actually it's, from the follower point of view, infeasible. Because I have to answer, the follower has to answer at the same time y1 and y2. And so this is a very bad news, because this problem here was extremely simple here, a very simple problem. And immediately when you try to handle this, you understand that the conjecture of player 1 on the reaction of player 2, of follower, and the conjecture of player 2 on the reaction of follower could be different, and that is not possible. That is a very big difficulty. So it is what occurs here. If my calculations are correct, it is what occurs here, and thus it means that even on a very simple problem, multi-leader single follower, we have only one follower here. Multi-leader single follower seems to be very, very well setted, very well posed, but actually it is really ill posed by nature. And so what is the conclusion of all those examples, all those bad examples? Well, I would say that if you go there, if you go to multi-leader single follower, pay attention in order to be sure that you don't have a ill posed model. Pay attention to the fact that for each x1, x2, you have a unique solution for your follower problem, a unique one. If you do that, then a lot of ambiguity, difficulties, and ill-posedness will disappear immediately, and things will be clear, and you can do correct things from a mathematical point of view, as well as from an economical or application point of view. But if you do not guarantee this uniqueness below, then you are really in trouble. So this is more or less the lesson of that. And of course, in this example, the difficulty comes from the fact that you have two solutions, two possible reactions, and that is very bad. So as we have seen, there are different ways to answer: selection, and even here, pay attention to the fact that here we are taking optimistic and optimistic in both situations, but it doesn't fix a problem. So you have to be sure to make to add some conditions, or to rethink your model in order to be sure that the lower level problem has a unique answer, a unique reaction of the follower for any x, that is for any x1, x2. In the case of single leader multi-follower, it is less tricky because actually here you have only one leader at the top. So you have only one conjecture of what will happen, and he agrees with himself. So there is no trouble in having this kind of multiplicity below, as soon as you precise what you want to do. But if not, then you can be in trouble. So if you have multiple solutions here, you have to precise here what you want to do: optimistic, pessimistic, selection, whatever. If you are in this context, then I really advise you to have some guarantees that you will have a unique solution, a unique answer, reaction of this follower guy. Okay. So I apologize again for the mistake into the initial function. And let's go. What I explained is one motivation to go there, nevertheless, was electricity market. And well, if you have a look to our model here, at least this one, there are plenty of them here in the different papers on that. The literature is quite huge. But if you have a look to this function here, what about the well-posedness of this problem? Is it correct? Is it well? Okay, here we are adopting optimistic point of view, but as we have seen, it's not sufficient to make this problem meaningful. But what occurs is that here this problem is in terms of Q. Q is a variable, Q1 to Qn. and this function actually, as soon as those are not only excuse me, oops, are those are not only strictly positive but strictly positive, then you will have here that this function is strictly convex, and this is a convex set. So you are safe. You have a unique answer for any AI, BI, for any couple AB. Actually, AB is a set. A is a set of linear part of the bidding. B is a set of quadratic part of the biddings. And thus, as soon as this vector is such that those BI are strictly positive instead of being positive or zero, then you will have the strict convexity, or you need at least one having a BI positive. So you will have a strict convexity of that and convexity, and thus you have a unique solution for this problem, meaning that it is not ill-posed. And since we put an optimistic, then we decide about what we want to do in case of, so of course, since we prove here, we have the property here that we have uniqueness, and then this is no longer needed, and optimistic, pessimistic, and everything coincide. By the way, another way, because, okay, look at that. It could be quite strange to impose that the BI are strictly positive, because it means that you cannot have linear cost, for example. That's bad. So in a work with Miroslav Pistek from Czech Republic, we considered the case where eventually BI could be zero. Why not? That was very interesting, very interesting studies, by the way, because we said, okay, well, assuming that they are forced to be quadratic is perhaps a little bit too much. So let us give the possibility that allow that B can be negative, can be zero, right? Of course, it is increasing because the bidding function, this is quite surprising, by the way, in electricity market, is that more you produce, the higher is the unit price. This is a characteristic based on the fact that more you produce, more expensive plants you need to switch on, switch off. So anyway, so but imagine that the BI can be zero, then you are in trouble here, because then this function is eventually not strictly convex, and you can have kind of full face of solution. So that could be very bad. And thus we had what we call equity property, which makes sense to my opinion. And equity property was the following: if two people bid the same function, then they will receive the same amount, they will produce the same amount of electricity. It's a equity. It's a rule for uniformness of the decision, I would say. So this equity property, we shown that it allows to have a unique solution of the ISO problem, or of the unique response, I would say, and thus that finally this problem is well posed. And very surprisingly, we actually proved that, okay, if you allow B to be zero, actually the optimal solution of this market problem will be with B zero. That is, the optimal solution are linear. So it means that if you put a strict, to obtain a strict convexity here, then you are missing the true solutions. So that's very surprising. We have been very surprised by this and verified a lot. And it is something like 15 pages of proof by hand. It's very technical things, but actually it works. And the very surprising thing is that the true optimal, the two equilibrium points are with linear bits. And thus you have to give the authorization of having zero here. And thus to obtain the well-posedness of your problem, you have to add another, an additional condition. And this additional condition was for us the equity property. So again, it means that if two people bid the same function, then they will receive the same amount. So this was the rule. So that was interesting because when you search in detail into the model and say, oh my God, this is not well posed. Okay, well, so I need a strict. Okay, but you cannot strict because this and that. And finally, you push. You finish by extracting some properties that you would not imagine before. So that's kind of interesting. Okay. Now I would like to speak about another application in which I invested a lot in the last years. It's called industrial ecoparks. So most of you probably don't know, absolutely don't know what it is. I will try to explain quite rapidly. So you are in a geometrical area, say a park, okay, industrial park, and you have different companies, 1 to n. And those different companies, they use some product. For example, speaking about water, this is the most simple to imagine, but as I will tell you, it's not limited to that. So imagine that a company, think about a paper factory. So paper factory need to buy fresh water, process, and then dirty water get out of the factory. So of course, this factory will pay quite high price for buying fresh water and for rejecting dirty water. Okay, right. This is life. I mean, if they want to produce, they have to use water and they have to pay for the discharge. Okay. So you have fresh water here. It is distributed in between the different companies, and this dirty water is going to the discharge point. Very good. Now, what is ecopark? The idea is very simple. Well, I mean, at least the idea is simple. The idea is what? You want to reduce the cost of production of each company. Clearly, they would love this. But you want also to reduce the environmental impact of the whole production. What does it mean? It means that you want to reduce the amount of fresh water coming in, and it is equivalent, to reduce the discharge water getting out. Because of course we assume that there is no loss of water on the tubes on the system. So you want to have an ecological impact which is lower, but at the same time, companies are not so interested by green things, except if they can save money. Or so if you want to motivate them to do this, to participate to this, then you have to guarantee to them a certain gain of cost of production or benefit or whatever. So how to do that? Well, this is okay. So yeah, in industrial eco parks, actually what is funny is that eco is at the same time ecological because you want to reduce the environmental impact, and economical because you want to reduce the cost of production of people. So how does it work? Well, you can eventually consider that the water getting out of the paper factory, okay, it is dirty, but not so much. And it can be eventually reused by another company for example, refreshing a system, refreshing a process. Or you can use eventually a regeneration unit to clean it a little bit and then send the water to another company. So in principle, it is very simple. The idea is instead that each company is sending this to the discharge, send it to your neighbor. Of course, the neighbor has no reason to accept this dirty water, except if he gains something, and gain something is money. So they will accept to play the game, to play the eco park game, if and only if they have some benefit, some positive benefit. So you can eventually, if the pollution at the exit gate is too high, then you can use eventually a regeneration unit. Of course, I would like to emphasize that this is not limited to water. One of the symbolic example of eco parks is Kallenborg in Denmark, where in the 60s it was only water, this kind of system, and now it is. I think that they are sharing today something like 45 different products: gas, ammoniac, vapor, water, many things. So it's not only simply about one product and one pollutant. It can be more complex than that. But here we will focus on water for simplicity, and also because it will I would say well for simplicity say. So again, the principle is that you will have some fresh water coming in some companies. We don't know which one, but anyway, for example, this one. And then this one will send to his neighbor company, and then it will go to the discharge. And the water can visit different companies before going to the discharge, or eventually go through a regeneration unit on the way, if after several use it is too dirty. Okay, so this is not a new concept. This concept has been investigated in the 60s, 60s, 70s, and a lot of publication. You can find a lot of publication on that. If you Google industrial eco park, you will find a lot of publication. So the thing is that, okay, so how the success will be guaranteed if each company save money compared to what we call the standalone. Standalone means you buy water, you reject water to the discharge. Instead of compared to the standalone, if you gain money, that's okay. And the eco park must generate a lower freshwater consumption or a lower discharge of water. So historically, from the very beginning, people wrote this problem, minimizing the freshwater consumption, right, or the discharge if you want, and as well as the individual cost of producer one, so on, and you have some constraints. Constraints are water balance, what is coming in is getting out, and so on. Topological constraint, because you have a network of tubes, so you have to take this, and quality criteria, which means that, for example, one company can accept a certain amount, percentage of pollution, but not higher than this, so you have to take this into account, of course. And the classical, very, very, very classical tool to treat this has been to compute Pareto fronts through multi-objective optimization. If you have a look to the literature in this topic of EcoPark, people are doing that. Multi-objective optimization, blah, 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 and then they press the button of Ant algorithm, or I don't know what, and for goal programming algorithm and scalarization of technique like that, and they have an answer, and it works in the sense that sometimes it reduces the pollution and reduce the cost. Sometimes, because of course you face always the same problem of multi-objective, is that you have a Pareto front, which means that you have different points, and you have to choose one. So to choose one, you have to add another criteria. And this is very sensible because it means that you go to the first company and you say, okay, well, we computed a solution, and we found this Pareto front, and we will take this point. And the first company told you, well, but I would prefer this other point of the Pareto front. It's better for me. And then you go to the second company, and this second choice of the first company doesn't fit. The second company doesn't like, and so on. So well, it's not so easy. So people from this topic came to me and say, well, we heard about your Nash or multi-leader follower techniques, and we would like to apply this. There is a team in Toulouse, which is the most powerful one concerning EcoPark in France. And they came to me and say, we would like to test your techniques about multi-leader follower games. I say, okay, I don't know anything about EcoParks. You are the specialist, but I know a little bit about multi-leader follower. So let's do this game. So and we tried, and okay, just to give you some calculation that they did. If you have 3 companies, you have a flow rate, so that was computed based on examples in the literature. This is classical example of the literature. And so those are the costs, fresh water plus discharge, reuse water, blah, blah, blah. And so here, the important numbers are this. This is the amount of water that the full EcoPark is using per hour in tons per hour. Of course, it's something like 300 tons per hour. It's not nothing. And the costs were this, 0.28, 0.16, and 0.54. In multi-objective optimization approach, what my colleagues from Toulouse, obtained as a better solution with a goal programming technique was that they obtained an ecopark structure. And thanks to this ecopark structure, there was a reduction of the total. It's not a big reduction, but it's in tons per hour, so it's not negligible. It's not so bad. But the difficulty is that this guy is very happy. This guy is very happy, but this guy will simply not come. And if you switch off these companies, then the ecopark is destroyed. So then, well, okay, you cannot satisfy everybody. So this I mean, the ecopark will not be built finally. So what we did is we said, okay, so we need a kind of independent designer. Because, okay, you have another problem with that. Look at that here. It means that actually the difficulty is that here to share the data with your neighbor, with the other companies. And usually companies are not really ready to share data, neither the cost of production nor the constraints that they have or the amount of production that they have. So this can be very difficult because they have to share things with everybody to commonly compute this. So first we said, okay, let's think about, you have an independent designer of the ecopark, and this guy will have access to the data, but through confidential contracts. So the company will be ready to give information to this guy, but through confidential interactions. And on the other hand, we have to find a fair way to consider this competition between companies, and the companies will not, by default, they will not cooperate. I mean, they will not share data or have a common decision, so it will be non-cooperative. And thus, immediately what comes is Nash game because of non-cooperation. And immediately, if you have an independent designer, what came is hierarchical optimization by level. So it means that actually the good tool to study this would be a mixture of bilevel and Nash game, which means multi-leader follower game. So we went in this direction, and I will not describe in detail the things, but if you think about, well, you have two possibilities. Either you put the leader, the authority, the EIP authority, which means the designer, either you put him in the model at the top, so at the upper level, and thus it is a single leader multi-follower, or you put him at the bottom, and then it is a multi-leader single follower. Pay attention to the well-posedness of your problem. Okay, so we tested actually both. I will simply say some word about single leader multi-follower because finally it has been the most effective, most pertinent concept. The single leader follower has been the most powerful one. So what is this guy doing? Minimizing the fresh water, taking into account the constraints. And the other one, they minimize their cost, subject to common constraints. For example, the water balance is a common constraint, a shared constraint, we say also, and so on. So here are, well, okay, so how to solve this? Actually, we were, okay, so what did we do? We were putting the KKT of that, plugging this into this problem. So we have MPCC, as said previously. And then we used the penalization method to take into account this mathematical programming. And this was solved in Julia meta solver, coupled with Gurobi, IPOpt, and Baron. And we were doing some sequential, I mean, solving with Gurobi, and then we have POpt and so on, and comparing the result and taking the better. So let me give you, so now it is with regeneration unit. So if you consider a regeneration unit in standalone situation, so here you have, well, okay, so regeneration is not so important because it's standalone here, so you can forget by that, but it's another example where the total of fresh water is 217, and those are the costs. And with the single leader multi-follower model, here is what we obtain. So this guy is happy, a very huge reduction. This guy is extremely happy also. Even more, this guy, and the more impressive thing is that now you need only 60 tons of fresh water per hour compared to the previous one. So, you know, with simply changing the tool, going instead of dealing with multi-objective optimization as it has been done for decades from the 16, we simply changed the tools. It was, to my knowledge, it was the first implementation of this technique in Ecobooks in the worldwide scale, and we obtain on academic examples those results, which are extremely promising. And I will go back at the end of this series of slides. I will go back to another approach that we implemented with David Sala and Cao Van Kien, which is rebounding on this work and doing another computation scheme. Okay, now let me give some things. Well, you can find those results in this paper of Jota last year, published last year with Anton Svensson. It is about single leader multi-follower games. So I will say some word about that. So first, an existence result. Try to find an existence result for multi-leader follower game, and you will not find a lot. There is very, very few, and in very particular cases, like, okay, assume that the functions are quadratic, that the constraints are linear, that we don't have orthogonality, and that this and that, then we have an existence. Here, we were looking for a general existence result, and actually, it is the first attempt, and there is a lot of empty space for new researcher, for young researcher in the audience, also for the old one, but anyway. The idea is simply to give a first existence result, general existence result for single leader multi-follower, which is definitely the simple case compared to multi-leader follower games. So if we assume that the capital F, let me recall, reminds that this is the objective function of the leader, the unique leader, and that for all the followers, the objective function is continuous, and that the constraint map here, given by this inequality, is lower semi-continuous set-valued map. So it's lower semi-continuity in terms of set-valued map with non-empty compact graph, this map. Then if the graph of the GNAP is non-empty, which means that for any x you have at least one GNAP at the lower level. So at the lower level you have this Nash game. The GNAP is the response of this package of player to the leader. And so if this map is non-empty and we have this lower semi-continuity of that, then we can guarantee that the single leader multi-follower game admit an optimistic solution, because here we have to decide if we deal with optimistic or pessimistic. Okay. Here I would like to emphasize an example that we built on a linear, so we cannot think about more simple. Well, as Martin and Ivana know, linear seems to be simple, but it's not. It is linear, and but actually have no solution, and it seems to be very simple. Here is a set of strategies convex. Here we have a GNAP of very simple linear things. I mean, y1, y2 with those constraints which are absolutely linear. And when you try to deal with that, actually what happened is that the GNAP solution, so giving x, this is the answer, the packages of a Nash, a generalized Nash equilibrium of the lower game. So if x is greater than 4, it is this. If x is between 0 and 4, it is this. Otherwise, it is anti-set. And then if you have a look to this is 5 max, 5 pessimistic. So no, yeah, well, yeah. No, wait. No, P, no, okay. So this is pessimistic because of the max, but actually it's max and max. So if you compute this, you will have this result. And finally, you will obtain that this map is not lowest semi-continuous. So you cannot apply lower semi-continuous in terms of functions. So you cannot apply the Weierstrass theorem. And it means that finally, you will not have a solution. And this is the pessimistic point of view here, because let me have a look here. We have min and max. So we are looking to pessimistic linear GNAP, single leader multi-follower, and this has no solution. So even if the example, again, even if the example is very simple, then you can easily face some situation where, and compactness and continuity, differentiability of the function, linearity, whatever you want, then you can face some situation where you have no solution to your problem. Okay, so let me go back now to industrial Ecobooks and present to you another approach. It's very recent. It has been accepted this year. It is a work done with David Salah, who presented a pitch, elevator pitch yesterday, no, on Monday, and and Calvin Kien, one of my PhD, former PhD. So the idea is that now we assume some hypothesis, some kind of simplification hypothesis. We assume that we have a unique process per company, because previously we were not assuming that. So eventually each company has different processes. And we assume a linearization of the generation unit, while usually they have a quadratic behavior, so concerning the price. So here we are linearizing or assuming that it is linear. And actually what we shown is that this single leader multi-follower game can be actually transformed into a mixed integer linear programming problem. So that is in a sense very surprising, because so initially we have a single leader multi-follower game, kind of complex thing, and now we are reduced in a sense to mixed integer linear programming. As Martin Labbé shown in the very first talk, this is from a complexity point of view equivalent to having a bilevel, if I correctly understood what you explained, Martin. So actually it means that from a complexity point of view, you went from a single leader multi-follower to a single leader single follower case, a simple bilevel. But the main advantage actually in this reformulation is that there exists a lot of commercial tools, for example, Cplex, for mixed integer linear programming. I'm not an expert of that, and I cannot claim that they are providing perfect solution and things like that. But anyway, at least you have already existing perfect tools, which is not the case, neither for Nash and definitely not for for single leader multi-follower games. You have to do everything by hand. So yeah, that's right. And then we treated this problem with Cplex and we obtained some results. And additionally, what we implemented, and that was not the case previously, is that we were looking for solution having at the minimum a certain rate of improvement of the cost. That is, if this is the cost of production, if you stand alone, if you are taking water, treating, rejecting water, this is your cost for a fixed amount of production, of course. And alpha is between 0 and 1, this will be the cost after the computation of the new Ecobooks. And we guarantee, for example, if this is 0.8, we guarantee 20% of gain to every participating company. So that's an enormous argument, because you go and the kind of commercial things, we start to be VIP, you know, not mathematician, but VIP, going to the companies and say, okay, come on, in my Ecopark, I can guarantee to you 5%. That's a very big improvement compared to the previous modelization, and in particular to the modelization through multi-objective optimization that, to my opinion, cannot do that. So, okay, so how does it work? Well, here is the key theorem of the things, is that actually the set of equilibrium the set of equilibrium of the lower level game between the followers, which means between the companies using water, can be actually described by this set of equation in equations. Well, that's the key point, because then you plug this into the constraint of the previous problem, and thus you have the upper level problem, which is simply minimizing Z is the total amount of fresh water. And you plug all those constraints in this, and you simply obtain well, it's not simple, but it's more simple, a mixed integral linear programming model. Well, what is E? Well, E actually is a topology of the network. So it means the tube. Do you decide to put a tube, blah, blah, blah. So in fact, it is kind of 0, 1 variable. So it's not only mixed integer, but it's actually Boolean integer variable linear problem. Okay, so here is, for example, a result that we obtain. This is a discharge. The ones that are in gray are consuming strictly positive water. So it means that all which are in gray, so there is 15 companies. Well, first important remark is that previously in the literature, if you have examples, due to the complexity of the model, people were treating with 3, 5 companies, not more. Here, thanks to the reformulation, we can treat very big ones. Well, very big. 15 is already big for Ecobooks, because it generates a lot of variables, of course, because well, anyway. And so here it was 15 companies. And all in gray, they are using strictly positive fresh water. So there is a connection of fresh water for each of them. And the white one, they are only using recycled water. So they are only getting water, for example, this one from 6, this one from 6, and this one also from 6 and 3. And thanks to this, actually, and here we were guaranteeing 5% of gain on the cost of production for each company, Well, you can tell me this is very strange. This is very strange, because imagine that I am not targeting 5%. 5% is not so bad, but let us be more ambitious. Can I do better? Well, you can think about, for example, 20%. Well, but probably you cannot reach this. That's true. You cannot reach this with the 15. If you guarantee a more interesting rate of reduction of the price of the cost of production, then some of the companies, the ones that are polluting more, will be out of the eco park. So the price to pay is to say, okay, if I want to increase this, I will automatically, exclude some companies, because they pollute too much. I mean, the water that they are discharging is too dirty. Nobody can want to use it. So how do you do that? You can do by hand, computing and having a look to all the possibilities of the things. We didn't. We did automatically. That is in the modelization. Actually, you have here. It is not clear, but you have act here, and this act mean active, which means they are in the market. They are in the eco park, and so this reformulation take into account the fact that the solution will not only give the amount of water that will go from one company to another one, but will also answer to the question: will this company be into the game? Or will it be excluded or not? And this is included into this actually notation that say if it is 0, this company will be out, and if it is 1, this company will be in. So it means that we are at the same time in the same mean LP problem, able not only to find the better configuration, network, and flow in the tube, but also saying that this company should be out and this company should be in. So just to give you some numerical results, so that was number of company operating standalone, because if you exclude some companies, then they will be standalone by force, because they are candidate to be into the eco park, but finally you said to them, no, 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 we want to guarantee a certain amount of how to say, a certain amount of gains, so we cannot include you. And so, of course, as soon as as soon as you increase the gain, that is, here I am guaranteeing 15%, 20%, 25%, you have more and more companies that will be out of the eco parks as a result. And this is, oh no, excuse me, this is the blue. This is the blue curve. And this is the global freshwater consumption. The price to pay also is that if you want to guarantee a better gain, then we will use more, well, actually, fresh water. So this is what we obtain, and this is, for example, for 0.01%, so almost no gain, but at least you guarantee some will gain, but some can have the same cost. And this is a curve giving here the global freshwater consumption and the number of enterprises. Okay, so here are some references on this topic, specific topic of eco parks. There are, as you can see, there are a publication not in Math Journal. This is one part of my CV is that I start to publish in industrial or process, I would say process journals, because those are really real applications that could have an interest. But on the other hand, you have very interesting math inside, and the concepts, as you have seen, are single leader, multi-follower techniques and computation and things like that, and they are not simple. And so they are very interesting from a math point of view also. So as you can see, one of my message in my slides is that you can have very rich interactions between people from real application and mathematician. The new application that people will bring to you, they will raise some new theoretical questions, for example, about the well-posedness, the stability, the existence result for some specific models. And on the other hand, when you have some result on theoretical results, you want to test them, it's very rich to go to people having real life application and to test if your assumptions are not too, I would not say ridiculous, but not pertinent to have real application. What we call application sometimes is simply application for us. It's toy problem. But when you go to a real application, you realize that, okay, well, we ask for the lower semi-continuity of this set value math, blah, blah, blah. But when do we reach this kind of application? So that's it for this part. Since I have a little bit of time, I will complete this with another part. So let me stop sharing this and go to another set of slides.
Didier?
Yeah.
Maybe before you do this, there was one question by Miguel in the chat.
Okay, let's go.
It was already maybe partly answered, but maybe you can give some more details. The question, Miguel is there. You can ask the question on your own.
Yes, hi Didier. I was curious, you were solving the model with wanting the same amount of reduction for every company. But I was going to say, well, if different companies have different amounts of dirtiness that they put into the water, maybe it would make sense to have different alphas for different companies. And could that be done?
Yeah. Actually, yeah. We made computation. It's not reported here, but we made computation with single alpha, uniform way, and multiple alpha. Multiple alpha is from a numerical and mathematical point of view more interesting. Definitely, I agree with you. But then you enter in a very tricky area because you have to go to the company and bargain with them a certain amount of reduction of costs.
Yeah.
So then to which one you will give the better one? To the small one, to the big one, to the, well, so yeah. From a political point of view, it's it could be kind of difficult to justify, except if you say, okay, some already implemented some ecological processes, blah, 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 already invested made some effort concerning the green things, so we will reward them, or at the contrary, they already invested, so we will push the other one to participate to reduce their pollution. So
Yeah.
except with this argument, otherwise, you know, from a mathematical and computational point of view, yes, I agree with you. Alpha I would be not alpha but alpha I, depending of the player.
Yeah.
But from a political point of view, you know, I would not be the guy bargaining with those companies.
No, that's a different job. But there would be also, if we turn it into alpha I, then there would be also the question of, is there a way to define some kind of welfare function and
Yeah.
argue that this is the optimal alpha I for each company, given this global welfare objective for everybody?
Absolutely. That would be a very interesting and a very, very interesting extension of what we did. Because yes, that could be actually turning those constant into variables.
Yeah. Basically,
Absolutely.
from a mathematical perspective, that would be the question.
Yeah, I agree with you. That would be great. But we were so proud of transforming the single leader follower into a mean LP that we didn't went further.
No. And I don't mean to say that the work that you haven't done is already quite something and interesting. But thinking from the point of view of the application, these seem to me natural questions to say. It's the usual, okay, you've done this. This is great. This is fantastic. Now, let me tell what I really want. I want something more. I always want something more than what you've done. This is just
that's normal. That's in spirit from real life, and that's what I like. I mean, interesting question, interesting theoretical question coming from inspiration from real life. Absolutely. And not simply from black or white board.
Yeah. Good. Thanks.
Okay.
Thank you.
Perfect. So there's one more paper on your to-do list, Didier, now, and you can go on with the slides that you wanted to share.
Well, some of my co-authors here present are already waiting for my participation to the common work. So, well, I will not engage in that. They will be. Okay, if I do that, I guess you can see the things here. Is it full screen? No, or what? Okay, so, okay, stop sharing and I will share the other one, excuse me. I guess it is this one. Let me try. Oh, what's happened? Okay, I didn't went out from that. Excuse me. I will close this one. Which one is it? Yeah. So I will close this one, share. So do you see my full screen now?
There is still the continue vignette at the side.
Okay. So forget about. Okay, stop sharing this. I will share my full screen. Yeah, this one. Okay, let's see that. Then I'll do that. All right? Is it full screen now?
Yes.
Okay. Perfect. So, I spent a lot of time actually in my career working on quasi-convex optimization. I like this. I would say even I love this. It is not that I don't like convex things, but a lot of progress and enormous and marvelous results have been obtained in convex functions, convex optimization. And there is a lot of space for new research and new topics for new improvement into quasi-convex optimization. So this is one domain in which some open questions are numerous. So for what I will present, my co-authors are, for example, Nicolas Gisavas from Greece. He was also in Saudi at the time. Miroslav Pisek from Czech Republic and Didier from Canada. So just I will how much I have? Well, okay, 35 minutes, so I guess it will be okay. I would like to introduce to quasi-convex optimization for those who don't know so much. So what is a quasi-convex function? It is a function such that you have this modified Jensen inequality. So instead of having here lambda fx plus 1 minus lambda fy, you have a max here. And this can be rephrased geometrically because this is very geometrical. You can rephrase this by saying that the sublevel sets are convex sets for all the sublevel sets. So imagine you have a function and you cut it horizontally, and you have a look to the pieces you obtain, the slides you obtain, and they are convex sets. So this is a quasi-convex function. Well, actually, if the function is differentiable, the function is quasi-convex if and only if the gradient or the derivative is quasi-monotone. And if you don't have differentiability, you have eventually a sub-differential in the sense you like. I don't know, Clark, Rockefeller, Mordkovich, whatever. And F will be quasi-convex if and only if the sub-differential is quasi-monotone. Well, actually, depending of the sub-differential you use, you will need some smooth property of the norm of the Banach space in which you prove the things. Because here my space X is a Banach space. So you could need here to obtain this equivalence some smooth property of the norm of the Banach space. Here is a perfect quasi-convex function here. So you have an open book here, and then a flat pot, and then a round thing, kind of part of ball. So what is quasi-convex? Well, actually, if you cut the things here, you cut horizontally. What do you obtain? You obtain those parts, those sublevel sets. And here, this is a flat part. And you have this. So the sublevel sets are convex. Yes, we can see that those sets are all convex. Right, very good. And we say that a function is semi-strictly quasi-convex if it is quasi-convex, and we have this strict inequality implies this one for any z in the segment. Broadly speaking, it means that a semi-strict quasi-convex is a quasi-convex without full dimension flat parts geometrically. So my main idea in the things that I developed on subdifferential for now several years, my main idea is that we used to consider derivative, gradient, or subdifferential if we don't have derivative. And my main message is, in the case of quasi-convex function, you have to forget about those tools. Why? Well, because essentially, if you consider the derivative or the coderivative of the subdifferential, they are normal cones to epigraph. They are defined as normal cone to epigraph. And if you go back to the definition here of quasi-convexity, the epigraph has nothing interesting for a quasi-convex function. Look at this epigraph. It is this graph, and you imagine the epigraph above. So it has no good properties. You have some corner, you have some well, bad things, flat parts and things like that. So the epigraph is bad, actually. It can be bad. Normally it is bad. For example, a classical quasi-convex function is a increasing step function. So think about the epigraph of the step function, increasing step function. Well, it's nothing. I mean, you cannot do anything with that. But where are the properties? They are not in x times r, that is the epigraph. They are in x, only in x. So don't have a look to this additional dimension to obtain the epigraph. Just have a look to the set x. And just have a look to the sublevel set. Because those sublevel sets are convex, so we have plenty of very good properties and very, very known results on the convex sets. So let's use that, which means forget about subdifferential, forget about derivative. They are not adapted to quasi-convex optimization. And so other arguments to go in this direction is to say, for example, if you have a look to the subdifferential, except if you use a Clark and your function is Lipschitz continuous and your set is correct, then you will have semi-continuity, upper semi-continuity. But in the other case, it will not be upper semi-continuous. And this is a minimum that you can ask to an operator if you want to solve, for example, variational inequalities. And even worse is that, well, well known, but for dreamers like me, it's not satisfying, is that if you solve the variational inequality associated to the subdifferential, which is necessary condition, then it's only necessary, definitely. It doesn't guarantee that the point will be a minimum. And my dream was at that time to say, no. I want an equivalence here, like in the paradise of convexity. In the paradise of convexity, you have solving the Stampacchia variational inequality or normal or necessary condition is actually sufficient. And you have, if you solve the variational inequality, you have a solution, global solution of your problem. And I would like this also for quasi-convex optimization. Well, you can say this guy is a little bit crazy because he's asking for things that actually is clearly known to be impossible. Variational inequality outside of convexity, it is loose of paradise, and you cannot go back. But my idea was I want to go back to paradise. So, you know, in the first slides, the first set of slides, I was in hell, and now I want to go back to paradise. Anyway, so what is the key for that is the normal approach. And this is very, very simple, actually. They're very natural. And this idea was not initiated by me. It was initiated by Jean-Pierre Crouzet from Clermont-Ferrand in France, who decided to have a look to the normal operator, that is the normal cone to sublevel sets. So you have the large sublevel set and the strict sublevel set, and you can make, you can consider the normal cone to the sublevel set at a point for the large here or for the strict, right? And he did some work. He defined this new operator, normal cone to sublevel set in a large sense or in a strict sense. The bad, and this is probably why he stopped to work on that, is that he was facing some difficulty because, for example, this operator is usually not upper semi-continuous, and thus, well, you cannot solve. Well, you cannot. It's difficult to solve some variational inequality if at least you don't have upper semi-continuity of the operator. And even well, so you can say, well, perhaps the large is not a good one. So let us think about the strict, the normal cone to the strict sublevel sets. But it is even worse because then you lose the quasi-monotonicity property, which again is very bad. So he stopped a little bit to work on that. For example, if you have a look to this function, very simple function here, it is quasi-convex. But if you compute this, you will see immediately that the strict normal operator is not quasi-monotone. This is simple calculus that you can verify on the slides that will be communicated. So the idea was a little bit different. We said, okay, well, we say with Nicolas G. Savas, the first progress in this was with Nicolas G. Savas. We said we want to make a mixture between both, because actually this one is always quasi-monotone, and this one is almost always upper semi-continuous. So let us take a mixture of those. And if we mix both of them, perhaps we put this into the mixer, we press the button, and we hope that the final juice will have both properties. Well, you have to mix in a specific way to obtain that, of course. And this is what we did. So we did by defining what we call the adjusted sublevel set and the adjusted normal cone. So what it is, very simple. You take the sublevel set, the classical one. Inside the sublevel set, you have the strict. You inflate the strict until you touch the point. So you take the strict sublevel set, you inflate it until you touch the point. You have thus a ball around the strict sublevel set, and you consider the intersection of both. Okay, it's a geometrical construction, and it is what we call new sublevel sets. They are adjusted. We call this adjusted. What is rho x? Well, simply rho x is the distance between the points you consider and the strict sublevel set. Because, of course, usually, if you are in a flat part, for example, then you are not, you don't touch the strict sublevel set. So one thing is that this adjusted sublevel set coincides with the classical one. As soon as you have that the closure of the strict is the large sublevel set. For example, when a function is semi-strictly quasi-convex. Okay. But we are not here to develop some tools for the class of semi-strictly. We are here to develop some tools for full space of quasi-convex function, general theory. So it's what we did. And okay, so yeah, so one first property, which is hopefully needed, is that F is quasi-convex if and only if the adjusted sublevel sets are convex. So we are back to the characterization of quasi-convexity thanks to sublevel sets. And now, since we have those new sublevel sets, we can simply define the normal cone to those sublevel sets. So you take a point, then you obtain the adjusted sublevel set, and you take the polar. And that's it. Point, you have what is called the adjusted normal operator. So let us have a look on an example. Here is my map again. Here are my sublevel set, and I will consider this point here, just at the end of the flat part, right? And I will, okay, so let me go back. What is the strict sublevel set? So the sublevel set for this guy, X here, the large sublevel set is this, everything here in this kind of part of disk here. Everything here is a large sublevel set. What is a strict? The strict is this, because you can see if you are here on the map, then the strict will be the set of points which are correspond to this part of the graph. Okay, so the strict is here. What do? You inflate this strict. This is a green lines. So you inflate it until you touch the point. Of course, here the distance between X and strict sublevel set is this distance. So you put a ball around this with a radius of this distance, and you obtain the green thing. Then you take the intersection with the large sublevel set, this one, and you obtain the blue thing. And now you do the normal operator by taking the polar to that. Well, it seems to be very simple geometrically. So then you have a new concept of sublevel set, and that's it. Just one remark is that previously the sublevel sets were depending, if you have a look to that, actually the sublevel set depends on the value of F. It is usually written as lambda. Lambda is a value. It doesn't depend on the point. It's a value. Here, people having the same value, for example, the points having the same value here, will not have the same sublevel set. So the sublevel set is associated to a point, not to a value. This is quite important modification, and actually this is the main modification. Okay, well, you can draw things and consider, for example, this very quasi-convex function, which is not semi-strictly quasi-convex, and draw things, blah, 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 blah. Okay, so anyway, I will not go into the detail. What are the properties? First, the properties is the following. Imagine that your function is lower semi-continuous, or even radially continuous, actually, on the domain. Or if you don't like radially continuous, you can assume that the domain is convex and the interior, and the domain is convex. And we also assume that the interior of the sublevel sets are non-empty for any lambda greater than, of course, the infimal value. Then what? Then the function is quasi-convex if and only if the normal operator is not reduced to 0. So the characterization of the fact that the function is quasi-convex comes from the fact that the normal operator contains another half line. Of course, it is composed of half line because it's a cone. So another half line than strictly the 0. 0 is a cone, right, but not so interesting and not carrying information. And actually what is said here is that if your function is quasi-convex, then you have the guarantee that your normal operator contains information, because not being 0, for any point that is not in the argmin. Have a look to the previous map here. If you have points on the flat part, you compute the derivative, you obtain 0. You compute subdifferential, you will have only 0. So loss of information. You have no real information. You cannot make a difference between this point and this point. Here, in this case, thanks to that, it says you have information carried by the normal operator. And additionally, this adjusted normal operator is always quasi-monotone. Okay, so with Nicola Agisavas from Greece already defined what is called upper sine continuity. It's a very low concept of semi-continuity. If you have semi-continuity, it is known that it implies hemi-continuity. Hemi-continuity is the upper semi-continuity on the lines when you restrict the map on the lines. And upper sine continuity is even weaker, okay? And what we obtain here is a local upper sine continuity of the normal operator map. So what is a local upper sine continuity? It is said that actually you have a restriction such that actually the map T, you reduce the map T to a neighbor at any point, and you will obtain an upper sine continuity with convex weakly compact values that is included into the operator T without taking 0. And what we obtain is that if F is lower semi-continuous and quasi-convex, with this non-empty interior property of the sublevel set, then this normal operator is automatically locally upper sine continuous on the domain, except in argmin, but if you are in argmin, it's done. And so what is the interest of that? Well, if you consider a minimization problem here, minimizing F over K, and K is supposed to be convex, very good. We don't care about K. K is convex, it's non-empty, very good. But we care about the function. The paradise was convexity. Then you know that finding some solution of the optimization problem is equivalent to find a solution of the Stumpf-Pacquiao variational inequality with the subdifferential, the Fenchel subdifferential, the classical one. Very good. Qualification condition, of course, but very good. In the quasi-convex case, it doesn't work. It doesn't work. You have a necessary condition, but it's not sufficient. So the main interest, and this is really, if you have to remember only one result, it could be this one. This one say, if you have, say, okay, just to simplify, assume that your function is continuous and quasi-convex. Okay, if you don't like radially continuous. Quasi-convex and continuous. And assume that, for example, C, the constraint set, previously it was K, now it is C, excuse me. C is included into the interior of the domain of the function. Okay, for example, your function is defined everywhere, so C can be anything. What do you have? You have that any solution of the Stumpf-Pacquiao variational inequality will be a global optimum of the function. This is kind of, I would say, brutal back to paradise. Why is it brutal? Because this is not explaining that it is if and only if, it is a sufficient condition. And even stronger is that here I don't ask C to be convex. C, what I ask to C is that the convex role of C is included into the domain. So if you have a function defined everywhere, I don't ask anything. This is extremely useful because if you think about bilevel problem and MPEC reformulation of bilevel problem, then you will minimize the function over a set with complementarity constraints. And those complementarity constraints generate a feasible set that is not convex, not with non-empty interior and bad things like that. But for this sufficient condition, no problem for me. I can take this C. It's okay for me, no problem. And I have a sufficient condition. So back to paradise. It's not magic. There is nothing magic in this. Simply the idea is we went to collect information where information is. For quasi-convex, information is on the sublevel set, and we went on the sublevel set, and we built a normal operator, and this normal operator gives us enough information to reach again this paradise of convexity. So this is the main lesson, the main message. When I say Stampacchia variational inequality, I'm speaking about the classical one. You know, it means that there exists an X star bar in the adjusted normal operator without zero. Of course, you don't care about trivial solution, such that you have this inequality. So it's a classical set-valued Stampacchia variational inequality. And so then we have a sufficient condition. Well, of course, we can think about a better paradise where we have if and only if. Well, you can obtain that if and only if, but the price to pay here will be that you will not have a quasi-convex, not only quasi-convex, but actually semi-strictly quasi-convex, which means that you do not allow full dimension flat part. Like, for example, if I go back to this one here, for example, here, this one, you have a full dimensional flat part. And in this one also, you have this full dimensional flat part, which means that it is quasi-convex, but not semi-strictly quasi-convex. So we cannot deal with that. If we want if and only if we want if and only if, we need semi-strictly quasi-convex. But this is just for fun, because what is useful is this one. We want to solve this optimization problem. What will we do? We will solve a Stampacchia. And any solution of this Stampacchia will be a solution of the global solution of the optimization problem. So that's more important, of course. What about GNAP? Because I will not stop here. You imagine, I will not stop to a single player and a single problem. So what about GNAP? Well, so if I consider now, well, the player I denoted by mu here, excuse me, could be I or mu anyway. So those are the adjusted sublevel sets of, so each player has a function theta mu, and those are the strategy of the other one. So here, of course, the sublevel set, they are in terms of the variable of the player. So they are the sublevel set here depend of the variable of the other ones, because we are in a Nash game. And if I denote by A mu x minus mu, the argmin of the problem of player mu, then I will consider the variational inequality defined by what? Defined by this operator f mu. Well, it seems to be a little bit complicated, but it's not. What do? We are in finite dimensional setting here. In Nash game, it is very often the case. If you don't consider dynamic things, usually by default, Nash games are in finite dimensional setting. But if you consider dynamic things, that is, the player are playing functions because of time, for example. So they have a strategy in time. Then, of course, you have to take into account that the fact that the variable could be functions. But here we are in Rn, and so I will define this n theta. It's a global operator, and this global operator is what? If I am at the argmin, if my x mu is a solution of my mu problem, then I will simply put the ball, close unit ball. And if I'm not at the argmin, what will I put? I will take the normal cone. I will cut with the sphere. So I have a cone. I cut with the sphere. So I obtain this kind of length, with no width. So this length, and I convexify this. So I have the cone. I cut with the ball. Then I have this length, and I convexify this. So you have the length here, and you convexify. Okay. So this is this set. So we define this here, and we define this normal operator. So it has non-empty convex values, compact also. And what's happened is that here, if we are, oh, now it is I again, excuse me. So if the function theta are continuous with regard to both variables, xi and x minus I, and quasi-convex with respect to the variable of the player I, so xi, then we can prove that every solution of the Stampacchia variational inequality is a solution of the GNAP. So now we have a Stampacchia variational inequality, of course, not in R and I, but in the product of the Rn1, Rn2, Rn, and so on. And but it's the same game. That is, you solve this Stampacchia variational inequality, immediately you obtain a solution of the GNAP. And again, it has to be emphasized that here we don't ask to capital X to be convex, neither convex nor compact. This is actually, this is coming, well, there is an important property here, is that when we do that here, when we do this construction, so we take the cone, we cut it by the ball, and we convexify. Actually, if your cone is too large, more than half a space, then what will occur is that when you intersect with the sphere and you convexify, then zero will be in. And it is exactly what we want to avoid. So we made a calculation on that, is that actually the only way for zero to be in means that you are at the argmin. So actually, if you are not at the argmin, then you will never face the fact that zero is in the this new operator. This is a proof here. It is based on Kara-Terodori theorem. Anyway, and this is a proof of the necessary condition. As you can see, it is very simple actually, because, well, of course we use this lemma, and then what is done here is that you consider the f mu. So f mu is here because we assume that we are not in the, if we are at the argmin, okay, done. If we are not at the argmin, we know that the solution here of the Stampacchia generate an element here, which is in this f. And then thanks to the lemma, we know that there exists a lambda such that we have this here for u mu being in the normal operator, mu. And then you have a look to the definition of normal operator, blah, blah, sublevel set, blah, blah, blah. And you obtain finally that it is a solution of the mu problem. And since it is for any mu, then finally you obtain a solution of the GNAP. So very simple proof. And concerning GNAP, what we obtain is the following, is that assuming that the function is continuous, again, symmetrically quasi-convex with respect to the I variables, assume that X, the set of the product of the constraint set, is assumed to be non-empty and closed set. This is the X in which you are doing the things. Okay, here I should make a comment. We are assuming here what is called the Rosen law. The Rosen law says that actually your xi of x minus I are given by the set of xi such that xi, x minus I are in a big X, that I call the big potatoes. So, so actually the xi of x minus I are slides of these big potatoes. And so if you do that, you have a big X, and if you assume that the big X is non-empty and convex, so under the Rosen law, again, so it's a GNAP under the Rosen law, then any solution of the Stampacchia will be a solution of the GNAP, and any solution of the GNAP will be also a solution not of the Stampacchia variational inequality, but of the quasi-variational inequality defined by the normal operator, and this key is defined as the product of the slides. So you don't obtain the potatoes, you obtain the box generated by the slides. The product of the slides is not the potatoes, is a box containing the potatoes. So actually we have this relation, but of course the most interesting one is this one. So here we have an if and only if you want, with the quasi-variational inequality, but the more interesting property is this one. If you solve this Stampacchia, then you will have a solution of your GNAP. Okay. And that, so you can find this work in, here you have the reference, the Operation Research Letter in 2008, done with Joy Dutta, where we applied the work done with Nicolas G. Savas to the case of GNEP. And now the next challenge is to do that for multi-leader follower games. So I can announce to you that with one of my PhD students, we already obtained some existence results thanks to this technique for single leader multi-follower games where the functions are quasi-convex. So we have some characterization, and thanks to a work that we have done with David Salah, we obtained some existence results for single leader multi-follower where functions are quasi-convex. So that's it for my lecture. Thank you.
Yeah, thank you, Didier, very much for these very nice talks. I mean, it was not even one talk, it was more than one talk. I collected some questions that we can take to the virtual coffee break. But before we go there, maybe because I think you did not read the chat, I want to close this session maybe with one comment on the lectures today from the chat. So I just read it out. So the lectures today have been a very good teaching education as well as the obvious interesting content. I really love how passionate Didier is communicating his work. Great work, Professor. Thanks. So I think with this one, we can really close this session. Thank you very much, Didier.
Thank you very much to you from all over the world.